Hi, and welcome to the sixth chapter of our lecture in soil mechanics. So, in this chapter, we'll talk about the vertical stresses in soils. And this chapter will be divided into two parts. First, we have the part where we discuss about the stresses caused by the soil itself, and for the latter part, we'll also discuss about the stresses caused by surcharge loadings in the soil. So, in this video, we'll discuss some definitions regarding vertical stresses, some stresses caused by the self-weight of soil, and we'll, um, we'll also be solving some example problems regarding the geostatic stresses. So we have the three terms: effective stress, denoted by sigma prime, the pore water pressure U, and the total stress sigma. First is we have the effective stress, which is also known as the intergranular stresses, and this results from the particle-to-particle contact of the soil grains. So for the pore water pressure, this is induced by the water um, in between the soil grains, and it is also known as the neutral stress. So if we combine the effective stress and the pore water pressure, what we'll get is the total stress sigma. So mathematically, we can write sigma is equal to sigma prime plus U. So let's now proceed to the stresses caused by the self-weight of soil. So in this scenario, we are assuming that the soil is fully saturated. So first is we have the total vertical stress, and this is equal to the weight of all material. So we are dealing with solids plus water per unit area above depth Z. So we can write sigma is equal to the saturated unit weight times the depth Z. So this is in SI, this is expressed in kilonewtons per cubic meter times the depth Z in meters. So what you'll get is kilonewton per square meter, or the unit of stress. So on the other hand, we have the pore water pressure. So we can get this as the unit weight of water times the depth Z. And hence, then the effective stress, sigma prime, is equal to sigma minus U. Or simply, the saturated unit weight times Z minus the unit weight of water times Z. So this one. And we can simplify this even further. So the saturated unit weight less the unit weight of water is equal to the effective, or the buoyant unit weight. So this is denoted by gamma prime times Z. So in geostatic stresses, we'll be dealing with different scenarios. First is we have the saturated soils without seepage, and then we have the saturated soils with seepage. So the seepage can either be downward or upward. And we also have the effect of capillary rise. So I bet you guys are familiar with capillary rise because you are already done with fluid mechanics. And yeah, lastly, we have the partially saturated soils. So in order for you um, to learn how to calculate the total stress, the pore water pressure, and the effective stress at different points in the soil. So let's have this. So for saturated soils without seepage, let's try to calculate the total stress at point A in this setup. So at point A, we have the total stress at A. So this is equal to the unit weight of water times the depth H1. And for the pore water pressure, so this is also equal to the unit weight of water times H1. So now our effective stress is equal to sigma sub A minus U sub A. So this is equal to 0. So because there is no soil above point A, so the stress will be, the total stress will be just from the pore water, pore water pressure. And also, the subscript here denotes which point are we dealing with. So, if that's point A, our subscript will be point A. So, now let's proceed to point B. So, the total stress at point B is equal to the unit weight of water times the unit weight of water times H sub 1 plus the saturated unit weight times H sub 2. And for the pore water pressure, U sub B, this is equal to the unit weight of water times H sub 1 plus, again, the unit weight of water times H sub 2. And for the effective stress at point B, so this is equal to sigma sub B minus U sub B. And then, so let's write. So we can cancel this one. And we are left with H sub 2 times gamma sat minus gamma of water. So this is equal to H sub 2 times the buoyant unit weight or the effective unit weight. So let's proceed to point C. So at point C, so we have the total effective stress. So this is equal to a unit weight of water times H sub 1 plus the saturated unit weight times the depth Z. And for the pore water pressure at point C, we have the unit weight of water times H sub 1 plus the unit weight of water again times Z. And so therefore, our effective stress at point C will be equal to unit weight times h sub 1 plus gamma sat times z minus the unit weight of water times h sub 1 minus the unit weight of water times times depth z cancel, and this is also similar with this one. So simplifying, we have z times the buoyant unit weight. So let's now proceed to the scenario where the saturated soil has upward seepage. So the saturated soil undergoes upward seepage. So let's get the three stresses at point A. So at point A, our effective stress sigma sub A is equal to simply the unit weight of water times H sub 1. While for the effective unit weight, while for the pore water pressure at A, this is also the unit weight of water times H sub 1. Therefore, our effective stress at point A is equal to 0. So as for our point B, we have the total stress sigma B. This is equal to H sub 1 times unit weight of water plus H sub 2 times the unit weight of water, or the saturated unit weight, sorry. While for the pore water pressure at B, this is equal to H sub 1 unit weight of water plus H sub 2 times the unit weight of water plus, since we have the upward seepage, we have to add the height h. So this is the head loss h. The head loss h times the unit weight of water. So therefore, our effective stress at B is equal to sigma B minus U sub B. We can cancel this term, and then so we are left with H sub 2 times gamma sat minus the unit weight of water minus the head loss H times the unit weight of water, or simply we can write gamma prime times H sub 2 minus the head loss H times the unit weight of water. So that's the effective stress at point B. So what if it's in point C. So at point C, we have the total stress sigma sub C is equal to H sub 1 times unit weight of water plus H, Z, not H sub 2. So, saturated unit weight times Z. So, for the pore water pressure, we have H sub 1 times the unit weight of water plus Z times the unit weight of water, and we'll have to do some ratio here. So, we have to get the I. So that will be equal to the head loss H all over the length, which is equal to H sub 2 times the depth Z times the unit weight of water. And getting the effective stress at point C, we'll have to simply subtract sigma prime C is equal to sigma sub C minus U. Sorry, this is point C, not point B. Minus U sub C. And then, if we do that, we're left with gamma sat times Z plus Z times the unit weight of water. Minus. Minus, and then minus H sub 2 times Z unit weight of water. So, we can simplify that. So, this sigma sub C is equal to Z times gamma prime minus the H times Z all over H sub 2 times unit weight of water. So, since our soil undergoes seepage, we'll have a limiting point. So, what if the effective stress is equal to 0? So, that case, we call that condition rather. So, we call that as the quicksand condition. So, I think you're familiar with this, but you don't know this exactly since we are only getting we are only getting started with the concept of vertical stresses. But so I bet you're guys familiar with the quicksand or kumunoy sat. So yun, kumunoy. And that's the case when the effective stress of the soil is equal to 0. And so that condition is called again quicksand condition or boiling condition. And And so let's try to so this is equal to 0, therefore, or Z times the buoyant, or the effective unit weight, minus the critical hydraulic gradient I sub C R times the depth Z times the unit weight of water. So when this is 0, we can get the critical hydraulic gradient as the buoyant, or the effective unit weight, all over the unit weight of water. So yes, so that's it. And the effective stress is equal to 0. That's the condition we call as the quicksand condition. And another, the seepage force F per volume of soil is equal to the hydraulic gradient I times the unit weight of water. So what if the saturated soil undergoes downward seepage? So obviously, since the direction of the seepage is different from the one we have discussed earlier, so the values of the effective, the pour water, and the the effective stress will also vary. So at point A, we have sigma sub A. So this is equal to H sub 1 times unit weight of water, and then our U sub A is equal to H sub 1 times the unit weight of water, and therefore again our effective stress at point A is equal to 0. So at point B, we have sigma times sub B. Sigma sub B is equal to H1 times the unit weight of water plus H sub 2 times the saturated unit weight. But our pore water pressure, B, is equal to H1 times unit weight of water plus H sub 2 times the unit weight of water minus the hydraulic gradient, or minus H head loss, rather, not the hydraulic gradient, H times the unit weight of water. So if we subtract the pore water pressure from the total stress, what we'll get is the effective stress. So this is equal to H sub 2 gamma sat minus the unit weight of water plus H, or the head loss, times the unit weight of water. So at point C, so again, sigma sub C is equal to H1 times unit weight of water plus Z times the saturated unit weight. For the pore water pressure at point C, we have H sub 1 unit weight of water plus Z times the unit weight of water minus, we'll have to do some ratio and proportion here to determine the head loss at point C. So yeah, the head loss at point C is equal to the H over H sub 2 times the depth C. Again, and times the unit weight of water. So our effective stress at point C is equal to Z, buoyant unit weight, plus Hz all over H sub 2 times the unit weight of water. And also, since this is head loss all over the length of flow, so yeah, we can write I is equal to H. Okay? And so that's it. So now we can proceed with the effect of capillary rise. So I think you're already familiar with this. So for example, we have some free water surface here and you attach some tube. Inside the tube, the water, the water level will increase at some point. So let's say the height H sub C, and this is our capillary rise. And if you will graph the pressure, so you will arrive with this diagram. And for soils, so this is your free water surface. So in our cases, that is assumed sometimes as the groundwater table. And then this one is the soil in a tube. So if you put the tube in here, the water level will rise up to this point. So H sub 1 is our height of capillary rise. And if you will plot the degree of saturation, up to H2 will be approximately equal to 100%. And it will decrease until point H sub 1. So according to Hazen, the height of capillary rise, so referring this figure, we have the H sub 1. So from Hazen. So I think he's the one with the Hazen-Williams formula from hydraulics. So the height of capillary rise is equal to a constant C all over the void ratio E times the effective size D10. So this is expressed in millimeters. And then at full saturation, we have the pore water pressure. the pore water pressure is equal to the negative unit weight of water times the height h. So RH is measured from the free water surface up to this one, H. And when partially saturated, so U is equal to negative degree of saturation all over 100. So you have to divide 100 when your degree of saturation is expressed in percent, but if in decimal, you don't have to divide that by 100 times the unit weight of water times the height h. So again, our h is measured from the surface of the groundwater table or the free water surface. So now let's proceed to the partially saturated soils. So according to Bishop et al., the effective stress at partially saturated soil, this is equal to the total stress minus U sub A plus X times U sub A minus U sub W, wherein U sub A is the pore air pressure and the U sub W is the pore water pressure. So Rx here will be equal to 0 when dry, and Rx is equal to 1 when saturated. So we're done with geostatic stresses. So what we'll do next is we'll solve 6 example problems. So yeah, let's have example problem number 1. So for the soil profile shown, calculate the total stress, the pore water pressure, and the effective stress at points A, B, and C. So yeah, so at point A, obviously, so at point A, obviously, our effective stress at point A is equal to 0 because there is nothing above point A that will cause some stress. And then also similarly for the pore water pressure at point A, that is equal to 0. And so therefore, our effective stress at point A is also equal to 0. How about for point B? At point B, we have the total stress. So this is equal to the dry unit weight of the sand, which is 16.5 kilonewton per cubic meter times 6 meters. So what we'll get is 99 kilonewton per square meter. And our pore water pressure at point B, this is equal to, of course, 0, because there is no water above point B and the sand is completely dry. And therefore, our effective stress at point B is equal to the total stress B minus U sub B. So this is equal to 99 kilonewton per square meter. Let's proceed to point C. At point C, we have the total effective stress, the total stress rather, sigma sub C is equal to 16.5 kilonewton per cubic meter times 6 meters plus the saturated unit weight. The saturated unit weight, which is equal to 19.25 kilonewton per cubic meter times 13 meters. So this is equal to 349.25 kilonewton per meter squared. So the pore water pressure at C, so this is simply equal to 13 times 9.81 meters and kilonewton per cubic meter. So this is equal to 127.53 kilonewton per square meter. And therefore, our effective stress at point C is equal to 349.25 minus 127.53. So our unit is in kilonewton per square meter. And this is equal to 221.72 kilonewton per square meter. So, regarding the first problem, we are asked how high should the water table rise so that the effective stress at C is 100 kilonewton per square meter. So, we are told to assume that the saturated unit weight will be the same for both layers. Okay, so in this problem, let x be our height of water table. And then we can write the equation. The effective stress is 190 kilonewton per square meter. This is equal to 16.5 kilonewton per square meter, cubic meter rather, times 19 minus x. Meters plus so if we subtract the buoyant unit weight so if we subtract wait, let me get my calculator.